Okay, we saw in the last section how to set up double integrals with rectangular coordinates. What we want to do now is we want to do the same thing, only we want to use polar coordinates, and we'll see that this is a pretty important thing to have for certain types of integrals. So let's start just by quickly reviewing polar coordinates. So we're used to giving points in the xy plane in terms of their x coordinate and their y coordinate. But we saw in calculus that we can also do this with polar coordinates. So the coordinates in this case are the distance r from the origin, so r is always positive, and then the angle theta measured from the positive x-axis. So these two things together determine our point x0, y0 uniquely. So any point can be given in terms of an r and a theta. And then some of the useful relations we have for polar coordinates here that will be useful for us are, well, the x value here, you see we could create a triangle if we drop the line here from the point down to the x-axis. And then the x value here would be a hypotenuse times cosine theta, so r cosine theta. And the y value would be y times sine. There should be an r here. It should be r sine theta. So this should be the value here. And then we also make use of the Pythagorean theorem here. We can get the x value squared plus the y value squared is the hypotenuse squared, so r squared. So those are some useful relations that will come up when we're working with polar coordinates. So some of the interesting things we get out of this, we know when we fix an x value, we get a line, or when we fix a y value, we get a line. In terms of polar coordinates, if I fix an r value, well, this is just all of the points at distance r from the origin. So it just gives us a circle centered at the origin. So for instance, if I take r equals 1, I just get the unit circle here. Now, if we fix an angle of theta, we just get a ray starting at the origin. So it's not a full line because it doesn't go in both directions. It only starts at the origin and goes out. So pictured here is the ray associated with the angle pi over 4. So those are kind of our base cases for drawing here, are circles and rays in terms of fixing polar coordinates. So now that we have a review of our polar coordinates, let's go ahead and switch to what we're really interested in, which is integration. So there are some situations where we don't want to work with rectangular coordinates. Polar coordinates will make things much, much easier for us. So for instance, suppose we want to evaluate the integral over the region R of some function f of x, y, dA, where we have this is our region R here. So you can see this would be a real nightmare to do in x and y coordinates because it's just going to be a mess because like if I want to do x first, for instance, I'm going to have one integral for this middle part where it hits this circle and exits on this circle, then a different one from here to here where it hits this line and exits on the circle, and similarly for here. And then also the limits are going to be a mess here if I use x and y coordinates because, for instance, when I enter this way, I'm going to get a square root of, say, 1 minus y squared, and then a 4 square root of 4 minus y squared. So you're going to likely have trig substitution integrals coming in. So it's really not something we want to do with rectangular coordinates. So what we'd like to do is rather than doing an iterated integral with dx dy or dy dx, we want to do this with polar coordinates because we can see this is a pretty nice setup here because the entrance point, if I were going out from the origin, would be r equals 1, and I'd exit r equals 2, and then I just have these are just part of the rays coming out from the origin. So I just have constant angles of theta as well. So let's go ahead and see how we can set up integrals using polar coordinates. So to do this, we want to recall our incremental areas we used to set up integrals first in rectangular coordinates. So in that case, we had our dA there was either dx dy or dy dx, and we chose that based upon which was more convenient for the integral we were trying to set up. And the reason that's how our dA came out was because if we looked at incremental area delta A, we could write that as delta x delta y or delta y delta x. And that's just pictured here in this square. If I'm looking at the incremental area of this little tiny square, it's just I have delta x here, delta y here, so it's just the product of those. And so that's how we did incremental areas for rectangular coordinates, and that's quite straightforward. Incremental areas for polar coordinates are not going to be quite so easy. So what we want to do now to do this in polar coordinates is we still want to take a little incremental area dA. We want to write this in terms of dr and d theta. So one of the things we're going to need from geometry is just the formula for an arc length on a circle here. So if I have a circle here of radius r, I take just a part of this circle, and the part of the circle spanned by an angle of theta, then the arc length here is r times theta. So this might be something you remember from geometry, maybe not. If you think of this in terms of the full circle, if theta was 2 pi, then this would just be 2 pi r for the entire circumference of the circle. So we're just taking a part of that to get this. You could also think of like, if I did pi over 2 here, then you'd be taking 1/4 of the arc or of the circumference of the circle and so on. So this is just a more general case of that. But we're going to need that because we're going to need this formula to find our incremental area. So what we have here is a picture of, we want to find, this is going to be our little incremental region we want the area of. So we're going to approximate this delta A, which is the area inside the solid blue lines here. We're going to approximate that in terms of delta R and delta theta. So we can see here, the length here, this is delta theta going across here, and the length to get from here to here is r. So this length here is r delta theta. And then we have some small incremental length going further than the r delta r. And now one thing to note here, of course, is I chose the delta r to be quite large in the picture, and similarly for the delta theta, just to make it easier for us to see. In reality, this delta theta would be something very small compared to theta, and delta r would be something very small compared to r. So this is just like kind of a blown up picture so we can see what's going on with everything. So now if we think about this, again, if this is very small, then we can think of this as, it isn't quite so spread out. It looks more like a rectangle here. And so if this were small and this looks like a rectangle, then we can say, well, one side of the rectangle is r delta theta, and the other side of the rectangle is delta r. And so the area of this is approximately r times delta theta. And again, it doesn't look like that on the picture here so much because I've exaggerated the size of delta r and delta theta. But you can imagine if these things get smaller and smaller, then this becomes more and more like a rectangle. So that's going to be our approximation. So then if we take the limit as delta r and delta theta get smaller and smaller, so we chop things up into smaller and smaller pieces, then my dA is going to become r dr d theta. And so this is a very important difference here. It's not dr d theta. We have that r in front of it, so it's r dr d theta. And that's because the bigger we are from the origin, the bigger this little piece will be. So the distance from the origin of our little incremental area here definitely depends on how far away from the origin we are. So that little area is dependent on distance from origin. So keep that in mind when we're setting up our integrals. So let's go ahead and look back at the integral that we had from above and see what this would look like in polar coordinates. So if we're setting this up in terms of polar coordinates, we almost always do dr and then d theta. It certainly is fine to do d theta and then dr, but it's just gonna turn out that most of the integrals we look at, it's gonna be much easier to do dr first and then d theta second. So if that's the case, we want to change our x and our y to polar coordinates. So x becomes r cosine theta, and y becomes r sine theta. The dA here becomes r dr d theta, as we saw from the last slide. And then my r is going to be some function that depends on theta, and another function that depends on theta. And then our outer integrals, remember, these always have to be just constants. So this will be a constant theta 1 and a constant theta 2. So it's going to be something like that for any region that we're looking at, r, if we want to set it up in polar coordinates. But now let's go ahead and look at our particular region we were looking at. So now we're doing dr first. So we think of fixing the value of theta and drawing a typical r. So this would be going out here like this dotted line. Now see, we enter the region when we hit r equals 1, and we exit the region when we hit r equals 2. So that means those limits are quite nice. It's just 1 to 2. And then this picture is a little stretched out here, but the theta is going to come down here and hit at this angle here, which for this region is going to be minus pi over 4. And think of this dotted line starting here at minus pi over 4, and then it sweeps up until it hits pi over 4 there. So we're going to go from minus pi over 4 to pi over 4 for our region here for our theta limits. So our integral becomes the integral over r of f of xy dA, Now, we still have the f of r cosine theta r sine theta because we didn't say what f was going to be. We have the r dr d theta. Now remember, my r limits went from 1 to 2, and then my theta limits went from minus pi over 2, pi over 4 to pi over 4. And so that gives us much nicer integration limits than it would have been for rectangular coordinates. And if you really want to convince yourself of that, you should be able to sit down and write out what the limits of integration would be if you used a rectangular coordinates on this. And just remember, you're going to have more than one integral for this. So you're going to have one integral plus another plus another. So wouldn't be a bad idea to go ahead and write those out. It demonstrates how much nicer it is to use polar coordinates, but it also gives you good practice on setting up a rectangular limits in about the worst situation you could possibly see. So that's it for polar coordinate integrals. We'll use these quite a bit interchangeably with rectangular and polar, depending on what the situation is and which setup works best for us.